Okay, so welcome back to the afternoon session. And the second talk this afternoon is by Professor Masafumi Udagawa. So Professor Udagawa graduated from Department of Physics of University of Tokyo, obtained PhD there, and he became the research associate at the Department of Applied Physics of University of Tokyo. Then since 2015, he has been a faculty at Gakushuin University, where children of imperial families study in Japan. Yeah, he was at first associate professor, then recent professor. And he also spent his time at Max Planck Institute for Physics of Complex Systems in Dresden as a visiting scientist. So Professor Udagawa has been very active in the field of magnetism, frustrated magnetism before. And recently he has been doing very interesting works on chiral magnet, which is very probably very fitting subject for this topic of the workshop, from theoretical concepts to experimental realization. And I think he is going to tell us about his work with this subject. Please, sir.
Thank you very much. Thank you very much for kind introduction, Professor Oshikawa. So, okay. So, and first of all, I'd like to thank the organizers to invite me as a prospective speaker in this workshop. My name is Masafumi Udagawa from Gakushuin University in Japan. And I'm really sorry I cannot join you on the spot in Kolkata for this wonderful workshop. This picture is actually from my photo book when my friend, Professor Arnab Sen, kindly invited me to IACS in 2018, if I remember correctly. It was a great time for me to spend a week in Kolkata city in this beautiful campus. Okay, so today I'll talk about our recent study on the detection of Majorana zero modes in Kita-Futsu chiral spin liquid. And before the talk, please let me introduce my collaborators. This presentation is a collection of the works listed here, featuring collaboration with Professor Roderick Messner in Max Planck Institute in Dresden, Shintaro Takayoshi in Konan University, and Takashi Oka in ISSP in Japan. And the most recent work listed here is in collaboration with Professor Fujimoto's group in Osaka University. And for this work, Masahiro Takahashi is a main actor. Okay, so the outline of my talk is here. The first part of this talk is a brief overview of the field, Kita-Futsu spin liquid. I will give a brief introduction to this system with a special emphasis of thermal Hall conductivity and appearance of Majorana zero mode. And the second part is about our work on the dynamics of Kita-Futsu model. In this part, we take up the integrable limit of this model and introduce an analytical solution of finite temperature dynamical correlation function of this system. With this solution, we address the dynamical response in the chiral spin liquid phase. And finally, in the third part, we address the possible role of charge degrees of freedom in Kita-Futsu spin liquid. Since a spin liquid is usually, we expect spin liquid is realized in an insulator, so charge may sound a little unfamiliar in this system. But we will propose to detect and manipulate Majorana zero modes by considering the charge response of Kita-Futsu spin liquid through the scanning tunneling microscopy. Okay, so let's start with the introduction. And, can you hear me well? Is it okay? Good. Okay, yeah, thanks. Then let me continue. So in this talk, we will consider Kita-Futsu honeycomb model. Since this system is quite well studied recently, some of you or many of you must be already familiar with this model. So this model consists of spin 1/2 defined on a honeycomb lattice, and spins are interacting with each other through the Ising type interaction with bond-dependent anisotropy. So spins want to align in X direction along the red-colored bonds. Meanwhile, they want to align in Y and Z directions along the green and blue bonds, respectively. Namely, if all the spins are aligned in X directions, then they satisfy the red bonds, but conflicts arise in blue and green bonds. As a result of this frustration, simple ordered states cannot effectively minimize the energy of the system. And instead, this model supports a quantum spin-rigid ground state as described by the exact solution, which we are going to describe now. Okay, to obtain the exact solution, the first and the most important step is to express spin 1/2 operator by Majorana operators. We introduce 4 Majoranas per each spin, C Majorana and 3 species of B Majoranas, and express each spin component by a product of 2 of them, with one additional constraint that the product of 4 Majoranas must be 1. So by adopting this representation, we can rewrite the spin Hamiltonian in a quadratic form coupled with static gauge fields. These coefficients, denoted by U, are the Z2 gauge fields taking plus minus 1, which are written as a product of neighboring B Majoranas. Remarkably, these gauge fields commute with Hamiltonian and also commute with each other. And for this reason, they are simultaneously conserved. Accordingly, once the values of all the gauge fields are fixed, you are left with quadratic Hamiltonian, so you can easily diagonalize it. However, this is not the whole story. We expressed each spin 1/2 operator with 4 species of Majoranas. This means the dimension of Hilbert space is doubly enlarged per site. And this problem appears as gauge redundancy. For example, if you multiply -1 with Majorana operators for one site at the same time, then this operation does not change the spin operator, physical spin operator, but the gauge fields change their values. So this means several sets of gauge fields correspond to one physically identical state. To remove this gauge redundancy, instead of the gauge fields, we consider their gauge invariant combination, namely, which is a product of 6 gauge fields around a hexagon, and classify the states in terms of them. Since this quantity takes, again, plus minus 1, we call it Z2 flux. And if you classify the states with these Z2 fluxes, you can eliminate most of the unphysical states. The final point is fermion parity. We express each spin by a product of 2 Majoranas. This means 2 Majoranas always come together, and you cannot make a single Majorana excitation. It imposes a constraint on fermion parity, so only the states with even or odd number of fermions, depending on the gauge choice, turns out to be physical. Okay, so all things considered, the procedure to obtain exact solution is divided into 4 steps. First, we fix all the values of Z2 fluxes, and second, you fix the gauge and determine the values of gauge fields. Third, given all the values of gauge fields, you diagonalize the quadratic Hamiltonian of C Majorana, and finally select eigenstates with correct physical fermion parity. after these 4 steps, you can finally obtain the complete eigenspectrum involving all the excited states exactly. Okay, then after introducing the derivation of exact solution, let me summarize its structure concisely. So to obtain the exact solution, we expressed spin operator by Majorana operators. And with this rewriting, the model can be mapped to the free Majorana fermions interacting with conserved Z2 fluxes defined on each hexagonal bracket. Since the Z2 flux is a conserved quantity, all the eigenstates are labeled by a set of their values taking plus minus 1. And in this classification, the ground state turns out to be belong to the simplest sector. Namely, all the Z2 fluxes take plus 1. So in other words, the hexagon carrying Z2 flux of minus 1 can be regarded as an excitation, and we call it Bison. So in this system, we have 2 species of excitations. One is a fermion expressed by C operator, and the other is Bison. So this is a concise summary of the properties of Kita spin liquid. And next, what signature can we expect in this quantum spin liquid state? Okay, the most remarkable property of Kita spin liquid is the appearance of chiral spin liquid state, which is stabilized by applying magnetic field as predicted by Kitaev himself in his original paper. For this chiral spin liquid state, we have 2 important predictions. One is the half-integer quantization of thermal Hall conductivity, and another is the appearance of Majorana zero mode. And in fact, the first prediction of half-integer quantization may have already come true in Kitaev's candidate material, alpha-arsenine trichloride. The low temperature phase of alpha-arsenine trichloride is the ordered magnet with so-called zigzag pattern. However, if you apply a sufficiently large magnetic field to destroy this magnetic order, the system becomes non-magnetic, and the half-integer quantized thermal Hall conductivity was reported there by Professor Matsuda's group. It implies the chiral spin liquid state is stabilized in this field-induced non-magnetic region. So still, the interpretation of this experiment is not completely fixed, and even competing experiments are coming on. But one promising and probably most exciting interpretation of this experiment is the formation of chiral spin liquid phase. Okay, so given the half-integer quantization is observed, the next issue must be the detection of Majorana zero modes. These 2 phenomena are 2 faces of the same coin, actually. In the chiral spin liquid phase, the Bison excitation accompanies Majorana zero mode, and it is expected to behave as non-abelian Ising-Ennion. In this light, its detection is not only a task of condensed matter physics, but is crucially important in broader context involving the research area of topological quantum computation. Okay, then what is the current experimental status regarding the detection of Majorana zero mode? Sorry. In fact, plenty of efforts have already been made to detect the Majorana zero modes. These are the collection of spectroscopic experiments conducted for alpha-arsenine trichloride in a magnetic field, ranging from Raman spectroscopy, inelastic neutron scattering, electron spin resonance, to terahertz spectroscopy. So all these experiments commonly observe multiple spectral lines, and it's a complicated reconstruction at the breakdown of magnetic order. So if the chiral spin liquid is realized close to this phase boundary, these spectral lines should contain the information on Majorana excitations as a result of the recombination of excitations. However, regarding this point, we could not reach a consensus yet. For the first two works, based on Raman inelastic neutron scatterings, they attribute one of the resonant peaks to the possible existence of Majorana excitations. However, the other two works do not. So one major reason for this discrepancy may be the lack of theory connecting the spectroscopic experiments and the presence of Majorana zeromodes properly. Okay, so for this reason, we first try to address the dynamics of Kita split and try to find a clear signature of Majorana zero mode in its dynamical response. Okay, so to address the dynamics, we especially focus on the low but finite temperature region, where a small but finite density of bosons are thermally excited, accompanying Majorana zero modes and interacting with each other. In this region, we can expect a dynamical response which involves the effect of Majorana zero modes, and it is relatively easy to extract the information of Majorana zero modes from the spectroscopic features. And to this aim, as a theoretical model to describe the chiral spin liquid state, we consider the ferromagnetic isotropic Kita model, supplemented with 3 spin interactions mimicking the effect of magnetic field. Kita used perturbation theory to derive this Hamiltonian, but we rather regard this coefficient kappa, which is supposed to be from the magnetic field, but we regard this coefficient as a phenomenological parameter to describe the excitation gap of this effective theory. In fact, it was pointed out that non-integrable, non-Kita interactions enhance its magnitude, and in the experiment of field angle dependence of specific heat, the magnitude of Majorana gap is not very small, not very perturbative. It is estimated to be of the order of 10 Kelvin. So we can regard this parameter not necessarily small, but we can take it substantially large. Okay, so in Majorana representation, the Hamiltonian is written as free fermions interacting with conserved Z2 fluxes or bosons. Then we use a classical Monte Carlo scheme by sampling the conserved Z2 fluxes and address the finite temperature properties of this system. Okay, so with this formulation, we calculate the spin correlation function from which we can extract a dynamical magnetic structure factor relevant to inelastic neutron scattering and other observable quantities. One important property of Kita model is that the spin correlation is extremely short-ranged. This property comes from the conserved nature of Z2 fluxes. So for example, if you apply the Z component of a spin operator at one site, then a pair of Z2 fluxes change their values on the both sides of the Z bond extended from the site. Or boson may, in different language, a boson shifts its position over the Z bond. Then for the spin correlation to be non-vanishing, we need to come back to the initial configuration after the operation of second spin operator. And this is why the correlation survives at most up to nearest neighbors. And in addition to this non-trivial constraint from Z2 fluxes, we also need to evaluate the fermionic propagator. Since this Hamiltonian is quadratic, at first sight, it may not seem like a difficult task to calculate this propagator. However, due to the change of flux configuration, the intermediate state, the intermediate part of Hamiltonian is different from the initial part of the Hamiltonian. And this brings about a difficulty. But a few years ago, we tried to overcome this difficulty and succeeded in deriving the following analytical expression for the dynamical spin correlation function. This expression still seems complicated and even contains the summation of G2 fluxes, so we need numerics to evaluate this quantity. But nevertheless, this expression is useful since it allows direct access to real-time and real-frequency representation of correlation function without analytical continuation. So our solution gives an effective approach to the equilibrium dynamics of Kitayfu's model. And beyond that, it has a potential application to time-dependent non-equilibrium problems. As a simple demonstration, this is the time dependence of the correlation function obtained from the analytical solution. At the relatively high temperature of 0.1 in unit of Kitayfu's coupling, the spin correlation decays immediately, only with small oscillation. However, at lower temperatures, the oscillation sustains for longer time. So our solution gives the information of dynamics on a real-time basis. And if you are interested in a spectrum in frequency representation, we can simply Fourier transform these functions numerically. Okay, then given the preparation so far, let me show you the results of our analysis one by one. Here I start with the thermodynamic properties of Kitayfu's model. The red point is a plot of specific heat, and the blue point is flux average. So it means if the flux line reaches, this blue line reaches one, there is no Wison left in the system. We also show the specific heat at zero magnetic field with a black line as a reference. So apparently, we have two energy scales in this system associated with Wison and fermionic excitations, and it is reflected in the double peak structure of the specific heat. The high temperature peak corresponds to the energy scale of fermions, while the low temperature peak is related to Wisons, where Wison density quickly decreases. Okay, then let's look at the dynamical structure factor obtained from spin correlation function. This is the result of a relatively high temperature region just below the fermionic peak of specific heat. The spectrum is still broad, and only some intensity accumulate at zero energy. And as decreasing temperature to approach the low temperature Wison peak of specific heat, the structure factor develops a peak, and we can even observe a multiplet of peaks below the main peak. And as decreasing temperature further below the low temperature Wison peak, we obtain a sharp resonant peak evolving at this relatively high energy. Okay, so given the momentum dependence of the structure factor is small for all the temperature range, let's focus on the zero momentum sector at this gamma point. Then focusing on the zero momentum, at high temperatures, the spectrum evolves only a broad peak around zero energy. And as decreasing temperature here, this broad peak turns to decrease, and instead, a sharp resonance peak quickly evolves at higher energy. And the most non-trivial place is in this transient temperature region, where we can find a multiplet of resonant peaks. This transient region corresponds to the low temperature peak of specific heat, where a small density of thermally excited bosons exist, accompanying Majorana zero modes and interact with each other. So this is the region where we can expect the response characteristic of the Majorana zero modes present in the system. Then how can we understand the origin of these resonant peaks obtained in this region? Okay, so let's look at this spectrum in the transient region with smaller temperature variation. We have 3 peaks in this low energy region. And firstly, regarding this low energy peak, remember that if you excite a spin, it makes a shift of 1 boson by 1 lattice space. Then if bosons are sufficiently far apart, distributed dilutely, this process makes no substantial energy change. And consequently, we obtain this zero energy broad peak. And since this peak assumes the presence of thermally excited bosons in the initial state, so it gradually diminishes as decreasing temperatures. Next, for this high energy peak, we can attribute it to the process of boson pair creation from the vacuum. This peak, in contrast to the low energy peak, evolves into a sharp peak as decreasing temperature. And the peak in between has more subtle origin. To understand the origin of this peak, we note that bosons have attractive interaction with each other, since each boson carries a Majorana zero mode in the chiral spin liquid state, and they have a fusion channel into one fermion, which has a smaller energy if 2 bosons are placed closer, and the Majorana wave functions have a larger overlap. So it means if 2 bosons exist next to each other, you need finite energy to dissociate them. And this dissociation process makes this intermediate peak. Okay, so summarizing, in this transient region, we have 3 peaks associated with boson displacement, boson pair dissociation, and boson pair creation. Okay, so briefly discussing the connection with experiments. In Raman scattering experiment, they found a growth of the peak.
Can I ask
Of course, anytime, please.
So please go back to one slide.
One slide, okay.
So I think the blue situation and the green situation are inconsistent somehow. So the blue station just assume the isolated boson.
Yes.
But the second green one, you assume that typically the boson appears.
Yes. Yeah, you are right. But if bosons are somehow distributed, some bosons are isolated and some bosons are close to each other. So yes, of course, the relative magnitude depends on the temperature, but both processes coexist.
I see.
Yes, at some temperature.
Okay. Okay. Thank you. And from the amplitude of the peak, we can understand the
exactly. Yes, the distribution of how to say boson interboson distance.
Okay. Thank you very much.
Thank you. Any other questions? Okay, so let me proceed. So briefly discussing the connection with the experiments. In Raman scattering experiment, they found a growth of the peak in the field-induced non-magnetic region of alpha arsenium trichloride. And they attributed this peak growth to the pair dissociation process of bosons we have just discussed. And this interpretation is very interesting. However, the continuous peak growth as lowering temperature implies a pair creation process rather than pair dissociation, according to my interpretation in the previous slide. So the connection between theory and experiment is not complete for this experiment, and it is also influenced by the factors like non-Kitaev interactions, which inevitably exist in realistic materials. So it is good to extract information of Majorana zero mode from the dynamical response, but it is desirable if there is more clearer criterion to decide if Majorana zero mode exists or not. Okay, so it is actually what we want to address in connection with the charge response of Kitaev spin liquid, and this is the third part of my talk. Okay, so to catch the Majorana zero mode, desirably, we want to do something like this illustration. If we can set up a sort of potential well that works on Majorana zero mode, then we can trap and control it as you like. However, it is easy to say, but difficult to do, since we have no coupling term available that connects single Majorana zero mode and local observables. This robustness of Majorana zero mode is usually considered as an advantage to protect quantum information of Majorana qubit. However, for the purpose of detection of Majorana zero mode, this robustness confronts us as severe difficulty. So to overcome this problem, we can take two possible routes. One is, rather than catching Majorana itself, try to detect boson, which is a vehicle of Majorana zero mode. And this is an indirect but sensible direction. And this is actually what we tried in the analysis of dynamical magnetic response. And another route is to use non-local probes. And we try to choose this direction here. Okay, so specifically to detect Majorana zero mode, we consider charge degrees of freedom. Why do we want to look at charge? Majorana zero mode does not couple to local observables. In this light, electron charge is of course a local object, but Kitaev spin liquid is realized in a good insulator with frozen charge degrees of freedom. So there might be a narrow chance that charge provides a way to locally detect the Majorana zero mode. Timely enough, several groups have recently focused on the role of charge in Kitaev spin liquid for the purpose of carrier doping or for the investigation scanning tunneling microscopy. And at the same time, several groups try to make a ruthenium trichloride thin film, which is necessary to probe Kitaev's sample with STM. Okay, for the purpose of detecting Majorana zero mode with the use of charge degrees of freedom, we consider Kitaev spin liquid in a setting of scanning tunneling microscopy as schematically shown here. So we put a sheet of Kitaev's material, for example, alpha ruthenium trichloride on a metallic substrate, and try to conduct electric current from STM tip to the substrate through the Kitaev system. We assume the sample and the substrate are in equilibrium with a common chemical potential set close to the upper edge of the lower Hubbard band of Kitaev's Mott insulator, considering the case of Hall injection. And we apply voltage bias between the STM tip and the sample and try to make an electric conduction. This is the basic idea. The advantage to consider STM is it may give us the information on local excitation energy spectrum. It is usually difficult to obtain in magnetic systems experimentally. In a general theory of STM current, the current is obtained as a convolution of a local density of states of the tip and system. So if the density of states of STM tip has no special structure, for example, it's constant in terms of energy, the differential conductance turns out to be proportional to the local density of states of Kitaifuchi sample. Accordingly, the crucial step of the analysis is to obtain a local density of states of Kitaifuchi system associated with charge excitation. Okay, to address this problem, we start with the TJ generalization of Kitaifuchi model by expressing spin 1/2 operator with its original fermion representation. Then, to obtain density of states, we introduce the whole Green's function of this model, defined by the operation of removing one electron from Kitaifuchi multi-insulating state and filling it in sometime later. Since we consider the vicinity of multi-insulating state, at the zeroth approximation, we may assume a heavy mass for the introduced hole and ignore the whole propagation within the sample. Then within this treatment, the whole Green's function can be obtained from the operation of creating one static hole in Kitaifuchi's model. And by applying the technique we developed to derive a dynamical response function, the corresponding whole correlation function can be analytically obtained as this form. And from this Green's function, we can extract the density of states. Okay, then let's move to the results. This black line is the local density of states without bosons. And this red line corresponds to the case where a single boson is present in the vicinity of the STM tip. These density of states are observable through the differential conductance. If you change voltage bias, the differential conductance changes like this. And if the boson is present, it exhibits two peaks, and it signals the presence of boson. Okay, so this contrastive outcome, single peak versus double peaks, demonstrate that the charge response is a quite useful quantity to identify the presence of boson. Okay, then what's the origin of different resonant peak structures? To understand this, let's look at the change of fermionic energy level structure by removing one electron. Firstly, in the absence of boson, there is a finite gap in the excitation spectrum due to the Majorana gap in the chiral spin liquid phase. We remove an electron from here, and by removing one site, then you will find one zero mode appears, which is attributed to unpaired Majorana. Since we have removed one site from the system, there remains odd number of Majoranas left locally. Then Majoranas cannot pair up completely anymore. And as a result, one unpaired Majorana is left in the bulk, and it forms a zero energy state. It means the injection of a hole practically introduces one Majorana zero mode in the system. In contrast, in the presence of one pair of bosons in advance, then there exists one Majorana zero mode attached to each boson, even before injecting a hole. In this case, the whole injection brings about a non-trivial result. The unpaired Majorana introduced by the whole injection close to one of the bosons pairs up with the initial zero mode attached to the boson and creates bonding and anti-bonding orbitals. It opens a new channel of electron conduction from the STM tip. Namely, when an electron transmits from the STM tip to the sample, it can excite a fermion in this anti-bonding orbital. And this resonant electron tunneling through the boson hole composite can be observed as this higher energy peak of the differential conductance. In other words, this double peak structure serves as a signal for the presence of bosons accompanying Majorana zero modes. Okay, the double peak structure of differential conductance or density of states gives clearly evidence for the presence of bosons accompanying Majorana zero modes. The difference of peak energies is equal to the bonding energies of Majoranas attached to bosons and unpaired Majorana introduced by whole injection. And this bonding energy roughly scales with fermionic gap in the chiral spin liquid phase. And according to the field angle dependence of specific heat in alpha ruthenium trichloride, the gap energy corresponding here, which is close to 10 Kelvin, so it is well within the range of experimental observation. Okay, so this is the end of the third topic, but we have recently one more progress. Today, I don't have enough time to discuss this topic, but with STM, we found we can access further non-trivial effects originated from Majorana zero modes. That is, the non-local spin correlation from carried by spatially distant Majorana zero modes can be detected by two-terminal STM. For this issue, please find an archive paper, which I think appears quite soon. Okay, so this is our theoretical proposal for the local detection of Majorana zero mode. And finally, with the rest of my time, let me quickly introduce our another recent attempt of real space manipulation of Majorana zero mode. Okay, in controlling the position of Majorana, we usually want to preserve its quantum information, since we want to use Majorana as a part of qubit for quantum computation. And for this purpose, the previous STM setup is not useful anymore, since it lifts the Majorana energy from zero and disturbs the stored quantum information. Accordingly, we consider a slightly different setup of STM for the purpose of manipulating Majoranas, where the chemical potential is set right within the charge gap. In this case, the magnetic exchange interaction is expected to arise between the STM tip and the Kitaifu's sample, and we can use this interaction to attract boson to STM tip. Okay, in order to set up a microscopic model for this situation.
Can I ask a question?
Please.
Could you go back one slide?
Okay.
So I think type materials are not exactly two-dimensional, right? They are more like quasi-two-dimensional systems, right?
Do you mean Kitaifu's system?
Materials.
Kitaifu's material. Yes, it is bulk material, but recently one sheet Kitaifu sample could be synthesized. So it's not a very unrealistic situation.
Oh, I see.
Mm.
So that is what you have in mind.
Yes.
Because in your cartoon picture, you have a thin film of Kitaifu system, right?
Okay.
So I was kind of confused. Yeah.
Yes, not thin film, it's one sheet film, one sheet sample of Kitaex system.
So what do you mean by the one sheet?
One sheet of that ruthenium layer is put on the some substrate like graphene. This is the system I have in mind.
You mean one layer of type system?
Yes.
Is that right?
Yes.
Thank you.
Okay. Yes. Okay, so let me proceed a little more. Okay, so set up a microscopic model for this situation. We first consider the STM tip as a non-interacting one-dimensional tight binding model and assume the exchange coupling between the STM tip and the spin in Kitaex sample closest to the tip. Then considering only the low energy degrees of freedom, the exchange interaction couples the electron in the tip to the position degrees of Bison. Namely, if the X component of exchange interaction is applied, the Bison shifts to the next hexagonal bracket over the X bond. And if the Y component of the exchange spin operator is applied, this Bison is shifted to here over the Y bond. So considering this picture, the exchange coupling connects the three Bison configurations around the STM tip. So this problem can be mapped to a spin 1 impurity condor problem by regarding proper linear combinations of these three Bison positions as spin 1, 0, and -1. And for example, in the strong coupling limit, this problem can be analytically solved. And the superposition of these three Bison configurations gives the energetically most stable state. And we further solve this effective Kondo problem numerically with the density matrix renormalization group method and evaluate the attractive energy between the STM tip and Bison by comparing the ground state energies in the odd Bison number sector and even Bison number sector. And the result is plotted here. So, assuming the energy scale of electron transfer integral is, for example, 1000 Kelvin, and realistic parameters for Kitaex coupling, like 100 Kelvin, the attractive energy turns out to be of the order of 1 Kelvin in the reasonably weak coupling region between the tip and sample. So 1 Kelvin is not very large, but it implies the possibility that we can control Bison in real space by using the STM tip as a sort of tweezers. Okay, so let me summarize my talk. We talked about three topics: dynamics of Kitaex model, detection of Majorana, and control of Majorana. In the first part, we introduced the exact solution of dynamical correlation function of Kitaex spin limit and demonstrated through the dynamical response of chiral spin limit phase. This solution enables us to analyze the dynamics of this model in real-time domain at finite temperatures. So I think this technology can be applied to much broader problems, including both equilibrium and non-equilibrium dynamics of Kitaex system. And in our second section, we showed that charge injection by STM can induce non-local action in Kitaex spin limit and makes it possible to detection the position of Majorana zero mode. And finally, we propose a way to control Bison in a real space by using STM as tweezers. And finally, please let me take a privilege as a speaker to announce the information on job opening for a postdoc. With the collaborators of this project, Takayoshi-san and Oka-san, I'm starting a project to combine quantum information technology and condensed matter physics. So if you are interested, please contact my email address. Okay, so this is the end of my talk. Thank you very much for listening.
Okay, thank you for a very nice talk and also so now the session is open for questions. Okay, there is someone is raising. Oh, okay, yeah. Please go ahead. Can you unmute and ask question?
Hello, am I audible? Yes, ma'am. Yeah, so the question I would like to ask, of course, you said it's a monolayer of, but there is also, of course, the chlorine atoms.
Sorry?
The chlorine atoms.
Mm-hmm.
The chlorine. It's
Chlorine, okay, yes.
Right, right.
So, okay, so
I don't know when you really make this thin film. I don't know whether they have gone to the monolayer. So what is the interaction of the STM tip with this chlorine? There will be some chlorine, right?
Yes, for the precise information, I want you to ask experimental professors. But if I understand correctly, it's a monolayer of octahedra of selenium chloride. That is, yes, that you can place it on a sheet, on a substrate of graphene or some other materials. That is the real situation.
So indeed, there will be these chlorine atoms, as you were saying, because the octahedral environment is preserved.
Yeah.
But then there will be some interaction between the tip and the chlorine.
Okay, yes, this is a good point. So it may apply the electric field to shift the position, for example.
Yes.
Yes. Yeah, that is possible. So yes, in that sense, yeah, we are considering a realistic situation, ignoring that effect.
Thank you.
Thank you.
Okay, thank you. Other questions, either online or from the yes.
Hi, Masa, this is Arnab here. So if you just go to your conclusion slide,
which slide? Sorry.
Conclusion slide.
Conclusion slide. Okay.
Yeah. So when you show this STM result and you have this double peak structure, if I understand correctly, you needed the fermionic structure to calculate these exact expressions, right?
Yes.
So if you move away from the Kitaev limit, is this double peak structure robust?
I think so, because it comes from the formation of bonding state between two Majorana zero modes. So if the presence of Majorana zero mode is guaranteed attached to Bison, so this effect must be robust. So if, in other words, if the chiral spin liquid phase is not broken, this effect should survive. That's my expectation.
I see.
Are you Arnab?
Yeah, yeah.
Ah, nice to meet you.
I have a question about your effective Kondo model. So in what sense is it spin 1?
Okay, it's why it's spin 1? Yeah.
Because your the exchange term just describes the coupling between spin 1/2 and the tip spin, right?
Yes, but effective low energy degrees of freedom in the Kita system is spanned by 3 states corresponding to 3 possible boson positions. This gives the 3-dimensional Hilbert space. Then I don't know
your spin.
I don't know the mathematical reason, but its interaction is concisely summarized as yes, a spin 1 Kondo problem.
So what is T?
T is spin effective spin operator in the
So in your 3-dimensional space, is that right?
Yes, yeah, and it satisfies the algebraic relation of angular momentum, so it is exactly this angular momentum operator.
Okay, yeah, thank you. Yeah, interesting.
Thanks.
Other questions? Yeah, so yeah, here you discussed the boson manipulation. And, so you can grade the Majorana.
Yes,
how to detect.
I hope to.
Okay.
Of course, there are many difficult problems to overcome, but I hope it's fast.
Why you need a postdoc?
Yes, if you are interested, please.
Questions, comments, online, on the lecture room. Okay, if not, let's thank Udagawa-san again.
Thank you very much.
Thank you very much for very clear. Good night.
Yeah, thanks a lot.
We reconvene at 5 p.m. for the final tutorial session.